Year 11. I'd like to just go over the AS1100 standards for bolts, nuts, and washers, and then I'll go through the exercise on page 25 and pages 28 and 29 of the Engineering Studies workbook. And Josh, just ask any questions as I go through. You can either type it in or you can just ask me. Okay, so let's have a look. This is a page in the yellow communications book. So if you can get this page, and I'll show you what page it is. I can't see it. Well, it's page 16. And what happens with these sorts of standards here, I'll just get this. Okay. Yeah, so what happens with the standards? With drawings, you don't want to have to dimension all nuts, bolts, washers, and things that have standard sizes. And so the idea is that you really, when you're drawing it, you use a standard that gives you the proportions of the nuts, bolts, and washers. And so the idea here is that if you've got a bolt, say you've got an M12 by 2, and the M means metric, the 12 means diameter, and the 2 is the pitch. And I'll just draw that for you, just to check. So if you've got a bolt, which is an M12 by 2, the M is metric, and we only use metric here. England and America use FPS system, but we use metric. So you won't have anything more other than metric in the HSC. The 12 is diameter, and you always show diameter by 5, as shown just there. And the 2 is the pitch, and the pitch is the distance between one peak and the next. So that there is the pitch. And if you go and buy a M12 by 1.5 pitch, it won't fit an M12 by 2 pitch. So you've got to know what sort of pitch it is. And so for every drawing that has nuts, bolts, and washers, you've got to learn these proportions here. So the thickness of the head of a bolt is 0.7D. So you multiply 0.7 by 12, and that means your drawing will be 8.4 millimeters, that distance there. And this is the thread here. You've got to know how to draw a thread. The outside line is thick dark, and this line here is supposed to represent the bottom of the thread, and that is a thin dark line. And the distance between there and there is the pitch divided by 2. So that's the thread depth, is the pitch divided by 2. So for this bolt here, that depth would be 1 millimeter. And this is D, the diameter, shown by that, and you get the diameter from that there. And across flats is 1.6D, and across corners is 1.8D. And the thickness of a nut is 0.8D. So you multiply 0.8 by 12, and so that will be 9.6. And this one here, the head of the bolt, will be 8.4. And the thickness of a nut is always bigger than the thickness of the head of the bolt, because the head of the bolt is in shear, and it the shear strength of a metal is quite high. And so the problem with a nut is because you've got a force pushing up against an incline of the thread, you're going to have a component pushing out there like that because of the taper of the base of the thread. And that's called the bursting force on a nut. And so you've got to have the nut thicker than the head of the bolt because of the bursting force caused by the angle of the thread. And then a washer is 0.25D, so it's a quarter of that. And the diameter of a washer is 2D. And in the HSC, when we used to mark it, if you have a washer and a nut, you always checked that the diameter of the washer was a little bit bigger than the cross corners of the nut. So that's the proportions, and you've just got to learn these. So there's 1, 2, 3, 4, 5, 6 things to learn, plus that, which is 7 things to learn, which isn't that bad. And I'll just go through all this up here. Make sure that you know how to show an external thread on a bolt or a shaft. You put a thin line there, thin dark, and a thick dark line there, and you taper it at 45 degrees, and you've got a thick dark line there, and you've got to make sure that you do according to this. And when you're looking at an external thread along the end view, this is how you show it. You draw, or you use your compass to draw a concentric circle on the inside, but you leave it broken. And normally you leave it broken in the top left-hand corner. And that's how to show a threaded rod or a threaded bolt when you're looking along that direction there. But internal threads, you show internal threads with hidden detail like that, but generally you don't show that, it's too much detail. But when you're doing a section, it's really important to show the section going through the threads. And so if this is a through hole here, as you see, make sure you put a center line there. And then if you've got a stopped hole in the section, the thread doesn't go all the way down to the bottom, even though you've got a tap called a plug tap, but it's still tapered a little bit. So you show the thread going only not right to the end. And this part here is the hole that was drilled. And this drill is the core diameter from the bottom of the thread on one side to the bottom of the thread on the other side. This is how you show an internal thread, an external thread on the bolt, is with the concentric circle cut on the inside. So that's an external thread. But an internal thread, you've got the thread cutting into the outside here, so that you show the internal thread with the external concentric circle with the gap in the top left-hand quadrant. And you just show a section like this, but I have never seen you do a section. You won't be asked that there. So make sure you know how to do a section. So this here, you've got thick, dark lines at the end. You're looking along here and you're drawing what you see there. Okay, now I'll just show you how to dimension this. So this is for a phi 12 bolt here. And just get out of this. Okay, so that's this is a phi 12 bolt here, and I don't know, did it say what the no, why should it for phi 12 bolt? I should have put what the pitch was there, let you know how to do that. Or actually, oh, it was already put on there. Okay, that's why it didn't show you the pitch. So this is the across corners, which is 1.8 times 12. And this is the thickness here, which is 0.7 times 12. And so you've got phi 12 there, which is the outside diameter of it. And this is 0.6D, which is 19.2. This is 0.8D, 12 eighths of 96, so it's 9.6. And the thickness is a quarter of 12, which is 3, and this is twice the diameter. Okay, and so this works with every size bolt. And as I said, you've got to learn all of this here. Now, the rule is that if you are only showing one drawing of a hexagonal nut, you've got to show 3 faces. You can't just show 2 faces. So you always have to show these 3 faces if you're showing only one drawing of the nut, which you are here, because this could be a square. So it's important, and you'll be marked down for that. So it's important that you do that. Okay, now let's go to these exercises that you asked me to go over. This is exercise on page 25, and so you've got a universal beam which is being supported on this hook here, and you've got to find the forces in these 2 slings. Now, it's really important when people, when they're slinging heavy weights or any weight on a building site, they have to have a certificate 1 on rigging up a sling on a weight, and the average tradesman that hasn't done the course, he's not allowed to touch it. No one's allowed to touch it, slinging weights, because you've got to have certification to do that. Because if you have this angle here greater than 60 degrees, you're going to put extra force in these sling arms, and I'll show you that in a moment. So this is how you do this question. There's the point. Everything's in equilibrium. It's not moving. So therefore, the force diagram will close up. And so you've got this 10 kilonewtons, which is about 1 ton, equivalent to 1 ton, is pulling up like that. And so you work out your scale. 10 kilonewtons equals 70, 1 kilonewton equals 7 millimeters. And so then you make this, then you're using your set squares. You make this 70 millimeters long, put the cents on it, and I generally use Bose notation. You don't have to if you don't want to. So I've got A there, B there, and C around on this sling here. So this force here going up here is little b, little c, and then you come around here, that will be CA. So that force there is parallel with that, but we don't know the length of it. And then we come around to this force here, and that force there is AB, and it's got to go through B. So you just continue that up there, and then you just measure off these distances, using that scale, and you can get the force in each sling. And I'll show you why you can't have this angle greater than 60 degrees. Like, let's just say, and I'll get this drawing, let's just say these slings were put out like this. One sling was put out there, the other sling was put out there like that. So this angle here is much greater than 60 degrees. Now, using the force diagram, you would have this one going out there, and you would have this one going parallel to it. I'll just guess at it being parallel. Okay, so what you've got here is this force in this sling, and this is the force in this sling here. And you can see that the magnitude of that, the force in that left-hand sling, is greater than the mass that it's lifting. And so that's why this angle here always has to be less than 60 degrees. And if you magnify this and you have it much greater than 60, and it goes out here somewhere, you can see that the forces in those slings far exceed the force of the weight force of the beam, and it's the force in the cable there. And so that's why you've got to make sure that you have that angle less than 60 degrees. Okay, let's have a look at this one. This next one I did when I visited you. Before I leave this, you can use graphical method, and you'll be getting 10% error here. Or if you form the triangle and you get all these angles, and you can use the sine rule here, and you can see that you have to get exactly the right answer to get the marks. And you can see that these values are pretty close anyway. My advice is to use graphical methods all the time. This one here, I won't go through this very thoroughly because I've actually done it for you. So this point here is a point that is in equilibrium. So therefore, the force diagram has got to close up. So I use Bose notation here. So I've got A between there, B between those two, and C between those two. And so you use a scale, 60 millimeters, 1 Newton equals 0.6 of a millimeter. And so you draw this 60 millimeters long. That's the weight force of the bike, which is 100 Newtons. And then name that force, which will be CA there. And then the next force that you come to is this one here, and that's AB. And that's got to go through point A because you know the length of that. And so you just transfer that angle through A, and it goes up at an angle there like that. And then we don't know how long that is because that's what we've got to find out. And so you've got to go back to this force here, which is BC, and it's got to go through C. You can see C there, and then you just continue that force down there. And you've got your force triangle here, and you just scale off these distances here using that scale, and you can get the force in that cable and the force in that cable. And they asked you to find the force in cable BC and CD, but because it's a cable, it can only have one force in it. So the force in CD is exactly equal to the force in BC. So that's how you do that one. And you can use the sine rule if you want to. You've got to work out all these angles here. But as I said, my advice is to use graphical, because graphical is quite easy. Now you've got to find, with this is a bracket, you've got to find the force members 1 and 2 here. And you know that that point is in equilibrium, and that's same as that point there, which is in equilibrium. And we've got a 500 Newton force, about 50 kilograms, equivalent to 50 kilograms, acting down there. So same routine. It's very repetitive, this, and once you do a few, you'll know how to do all of them. So, and you can only do this with 3 forces. You can't do it with 4 forces, because one of the forces will be indeterminate. And so, Bose notation here, you know there's a force in there, and there's a force in there. And so we call that a force. So we've got A goes between there and there, B goes between there and there, and C goes between that force and that force there. And so you've got to start with the known force. And I always make sure that you draw your diagram through the point of concurrence of those 3 forces, like that there and the one on the top. And then use your scale, which I haven't shown yet for some reason, because I've done it analytically. But anyway, let's use the graphical method. You select the scale, say 500 newtons equals 50 millimeters, so 1 millimeter was 10 newtons. And so you draw that down there and you make that a particular scale. Make sure you put the cents on it, and make sure you put your value there. And I like to name it. So this force here is AB, so that's little a, little b there. Then you come around, you've always got to read Bose notation clockwise. If you go that way, you're saying 2 + 2 equals 5. Always go this way. And so we go around to this force here, which is BC. It's got to go through B. It's got to be parallel with that. We don't know whether it goes up or down, so you just draw that line through there. And then we have to leave that, and then we come to the next force, which is CA. And we know that it's got to go through A there. And so you just produce it on where it hits this other force. There's your point of concurrence of these 2 forces. And so that will be BC. And you know that these arrows, the sensors, are directed by this force here. And so as you go around, the arrow, this tells you that it goes anti-clockwise. And so that will tell you what the force is in these members here, in the sense of it. And it will, when we do trusses, I'll be showing you how to work out what these forces are. So that's how you do those that you asked me to go over. And let's have a look at these questions on page 28 and 29. So what you had to do here is work out the weight, the mass that is used for this lever to keep it in equilibrium. Now, Josh didn't ask me to do this, but I'll do it again. I've done it before, but I did it using graphical methods when I was there visiting you. But he's asked me these 2, and I'll do those. there's one missing. I think it was the fishing one. But anyway, I'll go through this with you now, go through this, and I'll show you how to do it using analytical methods. Now, you know that a moment is always force times perpendicular distance, right? So you've got to know that a moment, and remember, a moment is equal to a torque, a twisting action, and a moment will only produce a rotational movement. And so a moment is equal to force times distance. But the distance has to be the shortest distance. It has to be the perpendicular distance. So see this here, they've given you those distances there, that distance there, which I can't see, and these angles here. And if you open your book at page 28, you'll be able to see those distances there. So I'll just show you how to do this analytically, and then I'll show you quickly how to do it graphically. So what you've got to do is, if you've got a point here, let's just say we've got point A, and you've got a force going down here like this. And let's say that is F. And you can't take that distance there. You can't take that distance there. You've got to take the perpendicular distance, the shortest distance, because that's what the definition of a moment is. And a moment has to be the force times the shortest distance on the perpendicular distance about the point of rotation. So here we have the point of rotation just here, and we've got the perpendicular distance is that distance there. And it's not a bad idea to show the examiner that you're taking the perpendicular distance, because if you get D2 wrong here, the examiner will see that you're taking the right distance. Now see that 10 kilonewton force, you have to find that distance there. And if you can't do it using trigonometry, you can use this scale here. They've given you that as 1,000 millimeters there, and you can say 1,000 millimeters equals, let's say, for example, 25 millimeters on your drawing there. And so, so you can say that 1,000, you can use scale, 1,000 millimeters is equal to what you've measured it. Let's say it's 50 millimeters to make it easy. So you've measured it to be 50 millimeters, right? And so then, therefore, 50 millimeters will equal 1,000. So therefore, 1 millimeter will equal 20 millimeters on the actual drawing. So if you measure this, that distance there, just say you can't work that out using trig, you measure that and say it's, if you've measured that to be 50, let's just say you've measured that to be 20 there, you multiply 20 by 20, and so that will be equivalent to 400 millimeters. And you can use, and if the examiner sees that you're doing this, you'll be immediately marked out of given 10% leeway. And that's only if you can't work this out. So you can use scaling to actually work these distances out, because all the drawings that you do are always done to scale in the HSC. Anyway, let's assume that you know how to use trig, and so we're going to work D2 out. Now, we know that that angle there is 30 degrees, and we know that this distance here is 1,000. The trig ratio that involves that and that is cos. So you say cos 30 degrees is equal to D2 over 1,000. Cos 32 is D2 over 1,000. So therefore, DT is 866 millimeters. So you found that to be 866 millimeters, and you'll find it exactly the same way there. You won't get it exactly 866, but it'll be within 10%. So we've found D2 there, and here's D1. It's a bit squiggly here, and you call that D1, and we know that distance there, which is 450, I think. 450, I can't read that there. And so we're going to use sine. That angle there is, well, if that's 30, this will be 60 here. And so sine 60 is equal to D1 over the hypotenuse, which is, oh, it's 400. 400, I couldn't read it properly. And so therefore D1 is 346. So the moment of that force has to equal the moment of this force to keep it in equilibrium, rotating about that point. And we've found the perpendicular distances there. See the perpendicular distance? And so you have to make a statement here. So this sigma means sum, the algebraic sum. We've got to use algebra because we've got to use positives and negatives because we're using vectors and that have sign. So let's say sum of the moments about B equals 0 with clockwise positive. I generally use clockwise positive, most people do. And so that's what all that means there. And so you take moments about here. So this is a mass, and we've got to find the mass, but we're going to use force and then just divide it by 10 to find the mass. So we've got M times D2, M times D2, and that is going to go clockwise, that in that direction, so it's positive, minus 10 kilonewtons times D1 equals 0. Now make sure you put it equal to 0 because that and that have to add up algebraically to equal 0. And now when we substitute, we know that. We've got one unknown here, so the mass is equal to 10 times 0.346 over 0.866. We've worked those out there. And so that equals 4,000 newtons. So the force down there will be 4,000 newtons. But read the question and it says what mass, because this is a washing machine bracket that they use in washing machines to stop the spin dry, and they have a mass on there. I don't know whether they do that with modern ones, probably not. Anyway, the old ones, they used to have a mass there, and so all you do is divide that by 10 to get how many kilograms it is. Okay, so the next one is the trapdoor one. So let's have a look at this. So the question asks to find the tension to support the trapdoor at that angle. And the idea is you've got the pivot point there, so it's all moments again. You've got the pivot point there, and because that's a cable or a cord, the force in that is equal throughout. So don't get confused. You think you have to find the force here, and you're asked for the force there, and you're thinking, Oh, is this force the same as that? But it is, because it's a cable. And so you've just got one force in the cable. So let's have a look at this. Weight forces always act through the center of mass. And so if I were you, I would put all the forces on the trapdoor to show the examiner that you know what's going on here. So you put a vertical force there, which is 120 newtons, and it goes through the center of mass. And remember, you're given this distance here, which is 3 meters. And so this distance up here will be 1.5 meters, but that's not the perpendicular distance. So you've got to use this little triangle here and find the perpendicular distance between that force and that pivot point there. Now you can use the same method that I used up here to use the scaling on the force on the diagram, because all the diagrams, as I said, are drawn to scale. But this is simple trigonometry, and you should be able to do that. And so I've got to find D1 here, and so we're using cos. Right, that angle there is 26 degrees. It tells you there. That angle there is 26 degrees. So cos is cos 26 degrees equal to D1 over the hypotenuse, which is 1.5. So therefore D1 is 1.35 meters. So the shortest distance between A and that weight force is 1.35 meters. Okay, now we've got a problem here too, because see, this angle here is 75 degrees, but we want it to be 90 degrees. And so it's really important for you to realize that you can't use that there, because all the forces have to be perpendicular. We're going to use that 3 meters there and get this force here, and then you know that the component, the horizontal component of this force will be cos. So it will be T cos 15, because 75 taken away from 90 is 15 degrees. So it's T cos 15. So let's do it. So we're saying the sum of the moments about A equals 0 with clockwise positive. So we've got 120 times D1, 120 times D1, and that's going to go clockwise. So that's positive, minus F times 3. Now we're finding F there. And remember, F is T cos 15. Okay, so you substitute your values. So you've got 120 multiplied by 1.35. So that's that 120 there, multiplied by 1.35. And that's going clockwise, so that's positive. Minus this force here. And that force, because of components, it's T cos 15. Okay, so you substitute T cos 15. If you want to, you can just use F there and then substitute it in as T cos 15 later, but it's best to put it in the equation here. So you've got T cos 15 multiplied by the perpendicular distance. There's the perpendicular distance because we made that 90 degrees, and that equals 0. And then you just work it out, and you've got 55.8 newtons there. Okay, but if you want to do it graphically, this is the graphical method of doing it. If you you've got only 3 forces acting on here. You've got 1 force there, 1 force there, and you've got to have a force through the pin there. And so you produce the weight force up until it hits the tension force in that cable. And then, so there's your point of concurrence. And then you just draw that up there. And so you've got the directions, not the sensors, but the directions of the 3 forces that are acting on this trapdoor. So when you've got the 3 forces, they're all concurrent there. And so I just use Bose notation. So I'll put A all the way, A goes all the way around here, because we're not worried about that force up there. We're just worried about the forces that are going into this point here. So A goes all the way around here, B goes between there and there, and C goes between there and there. And so you have to start with BC, because that's the one that you know. It's 120 newtons. Here's our scale here. So you draw that 120 units long. You name it. It is little b, little c. Go clockwise around here. This is your next force. Draw that force parallel with that one. We don't know whether it goes up or down. And so you just draw it in. And then the last force that you come to is AB. And it's got to go through B there. And so it's that cable there. And so you can work out, you just measure that distance there using that scale, and you can get pretty accurate. Look at that, 56 and 55.8 there. So that's the 3 force rule. Now I'll show you how to do this one up here using the 3 force rule. And let's have a look at it. So we know that there's a force between there. We know there's a force there. And we know there's a force there. So the first thing you do is you produce that on there. Then you, this isn't 100% correct. Produce that on there. And there's your point of concurrence. And then you join that to that. And so there's your 3 forces acting on that object. So now I'm going to use Bose notation. So I've got A, we always use capital. A goes between there and there. B goes there. And C goes there. Next thing you do is you start with your force diagram. You have a scale, and then you draw, and I won't put a scale in here, so I'm just going to draw that 10 kilonewtons to scale. And so, and that will be, and I won't change this, because I've got to change to the numerical value. So this force here is CA. The next force clockwise is AB, and we know that it's you've got to put the sensors on here. And this force will go up or down. No, it's a weight force, so it'll go down. And then the next force is BC, and I'll just draw this in. So this force here is CA, and the next force that we draw in is got to be concurrent with this. So I'll just draw this in there. It goes through there, and then so that should be A there. That's little a. And so this force here is AB. And we know that goes down because it's a weight force. And then this force must go up here. And that will tell you what the force is in the weight here, and which is that one there. Just scale that off. And it will tell you this difficult one to find mathematically. It will tell you the angle. You just measure that with a protractor. And that's the direction of that force up there. And you just scale this off and you've got the force that goes through that pin joint there. And you can see that it's quite involved finding these forces. Like we haven't found this force here. Over here, all we've done is found that weight force. But to find this force, we've got a lot more work to do over here. And so this is the way that I'll be doing it very graphically. But you've got to know the 3-force rule. So it's really important to know how to do the 3-force rule, because it's going to save you heaps of problems. Okay.